Good morning, students. Today we'll discuss some of the simulation experiments, that is using Matlab, some of the experiments which we are going to conduct today. Today, let us simulate a second order system and study the effect of P, PI, PD and PID controller on a step response. So before going into the experiment, first we should know what is a controller. A controller is a device which, when introduced, so it can be introduced in the feedback path or in the forward path of a system, which controls the steady state and transient response according to the requirements. So we know that time response will be divided into two classification. One is the transient response and the steady state response. So in order to control these transient and steady state response, so these controllers can be added either in the forward path or in the feedback path. Now, performance of the control systems can be improved by, so these are the controllers which we are going to add. So one is the proportional controller. So we are going to see simulation using Matlab, how the system, the transfer function behaves if a P controller is added. Then PD controller, that is proportional derivative controller, is added, and PI controller, that is proportional integral controller, is added, and combination of all the three, PID controller, is added. How it behaves. So first is, suppose without adding a controller, we are going to check how it behaves. Now consider a transfer function g of s equals 1 divided by s into s plus 1 and h of s is equal to 1. So here we are going to write the Matlab program for this transfer function. So OLTF, that is open loop transfer function, is equal to ZPK, means number of zeros, that is in the numerator, number of poles. P means number of poles. How many number of poles are there? Here we have two poles. One pole at s is equal to 0 and another pole at s is equal to -1, and k is nothing but the constant. So here within square bracket we are going to see write the value. So number of zeros, nothing is there, so you just leave as it is. Number of poles, so one pole is at 0, right? Then another pole is at -1, represent that as -1. Then constant k, so you can see the numerator k will be 1, so represent that as 1. Now close the bracket. Next, closed loop transfer function means you will be having one feedback, that is h of s is equal to 1. So feedback of, along with open loop transfer function, comma, your feedback h of s is 1, represent that. So here you are taking the step as the function, that is the input signal is step. So step of this closed loop transfer function you are going to write. Then grid, so in order to get grid in the waveform, you will be writing it as grid, and you need to display this title, that is title without PID controller. So we are going to write that as without PID controller. We are going to check how it behaves. Now directly we'll go for Matlab and then we are going to check how it behaves. You have three windows, you know, that is editor window is there, command window is there, and the workspace will denote whatever you have done, what are the parameters you have entered, that will be displayed. So in the editor window, so using script file, you're going to write the program. So same whatever I have shown there, you're going to write the open loop transfer function with zeros, poles and constant k. Then with the closed loop transfer function, the feedback of open loop transfer function comma 1 and step function of this closed loop transfer function and grid. So now you need to run this Matlab program. In order to run this, so you go to editor, then press run. So if you press this, you can see the
waveform. You can see grid has already applied. So you want the parameters to display. So you just click on all the characteristics like set length time, then rise time, then peak time, and the last is the steady state response. So just click on all the points. You can just get the time, that is, so here delay time will be, that is the 50%, you can just assume between 0.4 to 0.6, and the settling time. So this is the waveform for a given second order system without PID controller.
In the last program, we have discussed without adding controller how it behaves. Now with controller, that is with the P controller, how it behaves. So we can see here a controller KP will be added in series with the given transfer function. So what does this KP do? It increases the forward path gain by an amount of KP. So here by adding the KP value, so KP value should be properly selected. This KP increases the overshoot. So you can see in the waveform how the overshoot will be increased, whereas the steady state error can be reduced. So same program will run in the Matlab and check how it behaves. So you can see here with with the P controller. So we are going to add KP value, that is constant KP as 100. So now you are adding a controller. So right here controller is equal to KP. Next, so in the closed loop transfer function for the same program, you can just compare the earlier program with this program. Addition is one controller you're going to add and KP value will be added. And for the open loop transfer function, you're going to multiply this controller because you're adding KP just in series with the transfer function. Then same step of closed loop transfer function and grid, and what you want to display with P controller, how it behaves, you're going to you want to display. Next, run the program. So if you run the program, you can see how the waveform looks. So as we said,
the program, you're going to get P controller. So in this P controller, we can just click the characteristics like peak response, then settling time, then rise time, then the steady state response. So here in this P controller, we can see the oscillations will be more. It increases the oscillations. So this is what the waveform for P controller.
Yeah, next is PD controller. Means along with the P controller, you'll be having one derivative controller. Derivative, that is nothing but it is represented as S into KD. KD is nothing but again derivative constant. KP is nothing but the proportionality constant KP. So what happens if the derivative and proportional controller both are added for a given second order transfer function? Means the damping increases. So you can see the damping increases means the oscillations will be reduced. The overshoot of the waveform will decrease. That is what overshoot will be decreased, and delay time, that is the time taken, delay time will be for the 50, that is 10% to 50% of the time taken for the waveform is called as the delay time. The delay time will be increased. The delay time will increase. So this is the block diagram for PD controller. Now we'll see the Matlab program with PD controller. So here, what is the change you can observe in the program? KD value constant, it is taken as 50, KP as it is 100. So here in the controller function, since you are adding two controllers, you add KD comma KP. Okay, and rest of the thing, all the program will be same. Only thing is you'll be adding KP for the KP, you'll be adding KD. Okay. So if you run this program,
and this is the waveform for PD controller. In a derivative controller, we can see that the oscillations can be reduced. So we can reduce the oscillations. Same way here also, we can note down all the time specification characteristics. So if you click on all the points, we can get the exact value. So the delay time can also be found in between these two. So with this derivative controller, the oscillations can be reduced.
So with PI controller, what happens? It is nothing but a combination of, so a PI controller means it is a combination of proportional and integral controller. So when PI controller is added, the order of the system increases. Means if it is S square, then the second order system, it will be added to S cube. So third order system will be increased to fourth order. And the steady state error, that is ESS, is nothing but the steady state error that occurs at the end of the waveform, that is during the steady state response. We have two types of response. One is the transient response and the steady state response. In the steady state response, we are going to get the error, the difference between the standard value and the whatever you are getting. That error can be decreased and the system becomes less stable. If only PI controllers are added, the system becomes less stable, and here the KI must be properly designed to maintain the stability of the system. So this is the block diagram for PI controller. Now again we'll run and check the program. The programming is same, KP value is constant, so no change in open loop transfer function. Only in this while adding the feedback path, that is the controller, instead of KD you are adding KI. So KP comma KI. So the parameters means it is, these are Matlab case sensitive. In this Matlab, if you are adding capital KP, here also you should put KP. Then other than that, everything is same. We'll run the program and check how your waveform behaves. See here with the PI controller how it behaves. Means here you can see the steady state error. This error can be improved with PI controller. So, and also we can see what are the values you're going to get during settling time, rise time, peak time. Peak overshoot will be increased if you are adding PI controller.
Waveform for PI controller. So here this is the waveform for PI controller. So using this PI controller, also same way the overshoots, it increases the overshoots, and steady state error also it will go long, and the delay time can be reduced. So this is the waveform for PI controller.
The P controller, what is the change? By adding P and D controller, how it behaves, and by adding P and I controller, how it behaves. Now you are adding the combination of all the three controllers, PI and D controller, that is proportional, integral and derivative controller. So what does that P controller does? It stabilizes the gain and it produces steady state error. But this I controller, it eliminates the steady state error. But this D controller, what it does, it reduces the rate of change of error. So here we'll see how it behaves by adding these three controller using Matlab. What does the change? Only you're going to add KP 100, KI is 90, KD is 63. Okay. So there is no change in any of the programming part. There is no change. Only you are going to add the controller constants values, and in the controller there is transfer function of KD, KP and KI. You're going to substitute here 1, 0, and closed loop transfer function of feedback of controller, that is nothing but you're adding three controllers, that controller into open loop transfer function, 1. So here you're using step function as input, so that is why step of CLTF, and with the controller how it behaves, we just run the program and check.
We will be getting the smooth curve. So for this also, in this controller the oscillations can be reduced, so we can see the steady state response will be reduced, the rise time, everything will be reduced. We can get a smooth curve. So here you click on all the points, you are going to get the time characteristics. So by comparing this controller with all the other
smooth curve where the steady state error will be improved, stability can be improved. See here, one at step input of one, you are getting almost same waveform as per your requirement. Here also you can check the response, that is peak response, settling time, then rise time, then steady time. When you compare all these waveforms, you're going to identify and you can decide which controller is best suited for the application. Means which controller will take less time. By using out of these three controllers, you're going to make a tabular column where you're going to note down the settling time, rise time, and peak time, peak overshoot for all the three controllers, and we are going to conclude which controller is better. I hope I'm clear in explaining the Matlab program. Now we'll uh, go. Yeah, you can see here, you should make the columns like P, PI, PT and PID controller, and you're going to check settling time, rise time, peak overshoot, and this is delay time, and this is settling time and steady state error for different controllers. When you compare all these values, we can check that this PID controller will take less time. Sorry, this is your rise time. This is your delay time. Sorry, it is written TS. Then rise time. Then peak overshoot. Then settling time will be reduced, very much reduced when you compare with other controllers. Next, what are the advantages? So here, by using this PI controller, this increases the stability of the system, overshoots will be reduced, rise time will be reduced, and settling time will be reduced. So these application wise, these are used in control applications of in many industries to regulate the flow of oil or water, temperature control, pressure level control. These are used in many industries for operating for so many industries because of so many advantages of these PI controller. So these are used. So thank you students. I hope I am clear regarding explaining of these PID controller. Thank you.